Hello guys, today we are going to explain you about the mysterious forming of volcanoes 2,000 billion years ago.
Imagine a world where humans first looked upon a volcanic eruption. Night would be torn apart by rivers of molten rock, a glowing cascade sliding from the summit with terrifying grace. The air would shiver with the roar of escaping gases, clouds of ash blotting out the sun. Every lightning strike through the smoke would illuminate the terrified faces of those who watched, powerless against a force far greater than themselves. In such moments, fire and fury became gods, their judgment absolute. Across the globe, cultures interpreted these spectacles in the only language they knew, myth. In the Pacific, the Hawaiians worshipped Pele, goddess of volcanoes, the living embodiment of fire that created islands from the sea. She was feared as a destroyer, yet loved as a creator. In India, Shiva's fiery Tandava dance became a metaphor for both creation and destruction, the cosmic rhythm of life reflected in the earth itself. The Greeks told stories of Hephaestus forging fire in the belly of the volcano, a god of craft and chaos, while the Romans inherited these tales, adding their own reverence and dread. Lava flows, rich in minerals, created the dark, productive soils that would one day feed crops. Yet eruptions could wipe villages from the map in a single day, leaving only memory and myth to mark the loss. Life near volcanoes was a delicate negotiation with fire, a balance between the bounty it offered and the annihilation it threatened. One of the most famous early records comes from Pliny the Younger, a Roman author and lawyer who witnessed the eruption of Mount Vesuvius in 79 CE. His letters described the cloud of ash and pumice rising like a pine tree above the mountain, the darkness falling over the towns of Pompeii and Herculaneum, and the desperate flight of the inhabitants.
Pliny's meticulous observation laid the groundwork for what would later become modern volcanology.
He was among the first to note patterns in eruptions, to describe their stages, and to connect the sky, the mountain, and the trembling earth into a coherent narrative. Its dormant slopes offered fertile lands, while its summit remained a looming reminder of latent fury. In Iceland, volcanoes shaped the very identity of the land. Communities built their homes and livelihoods around volcanic soils, rivers, and geothermal springs, aware that beneath the surface, fire slept, sometimes peacefully, sometimes restlessly. Science, however, would only begin to interpret these phenomena in the last few centuries. Before the Enlightenment, volcanoes were often seen as portals to the underworld, evidence of divine wrath or instruments of fate. But careful observation, record-keeping, and systematic study gradually revealed patterns in the chaos. Geologists began to classify volcanoes by shape, eruption style, and location. Volcanoes were also agents of human history, not merely natural phenomena. The eruption of Santorini in the 2nd millennium BCE may have contributed to the collapse of the Minoan civilization, sending tsunamis across the Aegean and blanketing cities in ash. The eruption of Tambora in 1815 brought famine, disease, and climate anomalies that reshaped societies far from the mountain itself. Through these events, volcanoes became not just natural forces, but shapers of human destiny, entwined with culture, survival, and myth. The human relationship with volcanoes is one of awe and humility. While early humans could only watch and interpret, modern science has given us instruments to listen more closely, to measure the subtle tremors that precede eruptions, to analyze gases and ash, to map lava flows from space. Yet even with these tools, the core truth remains. Volcanoes are unpredictable, immense, and untamable. No technology can fully command them. No wisdom can fully appease them. They remind humanity of its fragility, even as they offer fertile ground for life and civilization. There was only fire, molten rock, and an atmosphere thick with noxious gases. The Hadean Eon, more than 4 billion years ago, was a world both alien and terrifying. Earth had just coalesced from the dust of the solar nebula, a collection of molten rock, metal, and ice, colliding in violent spirals. Meteorites struck ceaselessly, each impact scarring the surface, each strike stirring the molten interior. In this primordial chaos, the first proto-volcanoes emerged as cracks in the still soft crust, fissures through which the planet could release its inner heat. From these fiery vents, the gases that would become the atmosphere began to escape. Water vapor, carbon dioxide, nitrogen, traces of methane, and ammonia. Each eruption reshaped the surface, building early landforms, thickening the crust, and slowly forming the first fragments of continents. It is no exaggeration to say that without these volcanic breaths, the oceans themselves would never have formed. Rain could not fall, clouds could not gather, and water could not condense until the volcanoes had exhaled their primordial mists into the sky. And the story does not stop there. Underwater volcanoes, submarine vents along early mid-ocean ridges, created entirely new chemical environments. These vents spewed mineral-rich fluids into the nascent oceans, creating oases of chemical energy. Deep beneath the surface, far from the sun, these hydrothermal vents would one day become cradles for life. The first microbes, perhaps simple RNA chains forming in the warmth of mineral-rich water, owe their existence to the chemical complexity introduced by volcanism. Volcanoes, then, are not merely phenomena of destruction. They are planetary sculptors, architects of habitable worlds. Without them, Earth would have remained a molten wasteland, a barren rock orbiting the sun in silence. The paradox is staggering. Fire, in its rawest and most terrifying form, became the precondition for calm, for life, for everything that would follow. These processes continued for millions of years. Layers of lava built up, cooled, and fractured. Magma chambers formed, then emptied, causing the land above to collapse into calderas. Volcanic gases accumulated, sometimes triggering climatic shifts as the planet's thin atmosphere struggled to balance itself. Even at this stage, long before human observation, volcanoes were shaping the destiny of the Earth. They dictated the distribution of continents, the depth of oceans, and the chemical composition of the air and water. Imagine standing on such a world. Imagine the sky glowing with fire reflected from molten rivers, ash falls like snow, scorching and abrasive yet essential. Every eruption sends chemicals into the atmosphere, forming the clouds that will eventually temper the relentless heat. Volcanoes are not simply geological features. They are breathing organs of the planet. Through them, Earth inhales energy from the interior and exhales life-giving elements into the environment. The mystery deepens when we consider that these processes are not unique to Earth. Across the solar system, planets and moons display volcanic activity in forms both familiar and alien. Io, a moon of Jupiter, is scarred with sulfuric volcanoes erupting incessantly. Mars bears the colossal Olympus Mons, the largest volcano in the solar system, frozen now but evidence of a once fiery interior. Even icy moons like Enceladus and Europa exhibit cryovolcanism, erupting water instead of lava. Volcanoes, it seems, are not an earthly quirk. They are a universal mechanism of planetary life. The Earth, in those first tumultuous million years, had already learned to tell its story through fire. And though no eyes were yet there to see it, no minds yet to comprehend it, the narrative was set. A story of chaos and order, of destruction and creation, of fire and life. Volcanoes, in all their terrifying beauty, had begun the long work that would eventually make our world possible. For millennia, volcanoes were gods, demons, and storytellers. Their fire was worshipped, feared, and immortalized in myth. But as humanity's understanding of the natural world deepened, one of the earliest pioneers was Georges-Louis Leclerc, Comte de Buffon, a French naturalist who sought to explain the origins of Earth through observation and reason. Buffon argued that Earth had cooled from a molten state, and in his vision, volcanoes were not acts of divine wrath, but natural consequences of this cooling. Lava flows, he proposed, were evidence of the planet's fiery interior slowly releasing its energy. In the late 18th and early 19th centuries, volcanology gained momentum as explorers and scientists began to climb, measure, and describe volcanoes systematically. Alexander von Humboldt, a towering figure in natural science, ventured into the volcanic landscapes of the Americas. Charles Lyell, the great British geologist, also advanced this understanding in his seminal work, Principles of Geology. He emphasized the principle of uniformitarianism, that the processes shaping Earth today, however slow or dramatic, had operated in the past as well. Lava flows, ash deposits, and caldera collapses were not singular events but part of a continuum stretching across deep time. Volcanoes, once inscrutable, began to reveal their patterns, rhythms, and logic. Perhaps most poetically, Charles Darwin encountered volcanoes not as a distant observer, but as an intimate witness during the voyage of the Beagle. On the Galapagos Islands, in the Canary Archipelago, and in South America, he climbed volcanic slopes, observed lava flows, and documented the layering of ash and rock. He realized that volcanoes were storytellers, preserving in stone a record of Earth's slow evolution. Each eruption, each cooling layer of lava, was a paragraph in the geological narrative, waiting to be read by those patient enough to decipher it. The 19th century also witnessed the first attempts to classify volcanoes. Geologists noticed patterns in shape, composition, and eruption style. Stratovolcanoes with steep, conical peaks produced violent eruptions, while shield volcanoes with broad, gentle slopes allowed lava to flow in slower, more predictable rivers. Cinder cones, domes, and fissure eruptions were distinguished, catalogued, and described. Volcanoes were no longer mythical arbiters, but dynamic systems with observable characteristics and behaviors. Beyond classification, scientists began to understand the connection between volcanoes and broader geological processes. The recognition that volcanoes were concentrated along certain belts, later understood as tectonic boundaries, suggested that they were linked to the movement of Earth's crust. Volcanoes were not random anomalies, but manifestations of deep planetary mechanics, rising to the surface where pressure, heat, and molten rock converged. During this period, volcanoes also inspired profound philosophical reflection. Poets, writers, and thinkers recognized them as symbols of duality, destruction and creation, chaos and order, fear and fascination. Mary Shelley's imagination, for instance, was shaped by the awe-inspiring power of nature, including volcanic landscapes, which mirrored the turbulent forces within humanity itself. Volcanoes became metaphors for the human condition, forces we cannot fully control, yet forces from which understanding and growth may emerge. The awakening of scientific volcanology marked a shift in human perception. No longer were eruptions merely terrifying spectacles. They became opportunities for observation and discovery. Instruments were rudimentary by modern standards. Thermometers to measure heat, barometers to gauge atmospheric pressure, and simple chemical tests to analyze volcanic gases. Still, these early studies laid the groundwork for centuries of knowledge to come. For centuries, volcanoes were studied as isolated phenomena, majestic and terrifying, but still seemingly random. They erupted along mountains, islands, and coasts with no apparent rhyme or reason. Their locations were recorded, their eruptions measured, their lava flows mapped. Yet the underlying order of the Earth remained invisible. It was a puzzle that eluded the greatest minds of the Enlightenment and the Industrial Age. Why did volcanoes cluster in certain regions? Why did some parts of the Earth remain eerily calm while others boiled with continuous fire? Why did islands emerge from the sea in lines, and mountains rise in chains along distant coasts? For a time, the answers were cloaked in mystery. Volcanoes were often explained as consequences of the planet's cooling, or as relics of divine will. Scientists such as Charles Lyell, Humboldt, and Darwin had observed the patterns, but the mechanism remained elusive. The Earth, it seemed, had secrets too deep for casual observation. The 20th century, however, brought a revelation that would shake geology to its core. It began with an idea so radical, so counterintuitive, that it was dismissed by much of the scientific community. Alfred Wegener, a meteorologist by training, proposed the theory of continental drift. In 1912, he suggested that continents were not fixed, but slowly moved across the globe, drifting over the deep ocean like icebergs in a vast, unseen current. At first, his theory was met with skepticism. How could continents, some thousands of kilometers across, float on a planet whose crust seemed solid and immutable? Critics ridiculed the idea, calling it impossible, absurd, even heretical. Yet Wegener had evidence: the jigsaw puzzle of continental shapes, fossil correlations across oceans, and geological formations that matched across continents, now separated by vast seas. Volcanoes, though Wegener did not fully understand their role, were silently offering clues. The Pacific Ring of Fire, a horseshoe of eruptive activity encircling the ocean, traced the edges of continents and oceanic basins. Chains of islands, like the Aleutians or the Japanese archipelago, hinted at the movements of the Earth's surface. Volcanoes were not random. They were signals, markers of forces unseen, of energy coursing through the depths of the planet. It was not until the mid-20th century that the full picture emerged. The discovery of seafloor spreading revealed that the Earth's crust was not a solid, immobile shell, but a mosaic of plates, slowly shifting over the molten mantle below. Mid-ocean ridges spewed new lava, forming crust, while subduction zones consumed it, sending it back into the fiery interior. Volcanoes erupted along these boundaries, tracing the edges of tectonic motion. Plate tectonics provided the key to the mystery. Stratovolcanoes, shield volcanoes, and volcanic arcs were no longer isolated oddities. They were expressions of the planet's restless heart. Subduction zones, where one plate dives beneath another, produced explosive volcanoes capable of shaping continents and triggering mass extinctions. The shock of this realization was profound. Earth was alive in a way previously unimaginable. Volcanoes were not merely destructive forces. They were symptoms of a living, breathing planet. A planet that recycled itself, built itself, and reshaped itself over millions of years. The Earth was not static. It was dynamic, restless, and unknowable in its entirety. Einstein's theories of relativity may have described the vast cosmos, but volcanoes revealed the dynamism of the world beneath our feet. While stars moved across the sky and galaxies collided over billions of years, the Earth itself churned with energy, with fire, with life-forging destruction. Volcanoes were the visible pulse of that inner energy, a reminder that motion and change were constants, not just in the heavens, but here, in the soil, the rocks, and the very crust on which we live. Volcanoes are often celebrated for creation, for shaping continents, fertilizing soils, and seeding the oceans with the chemistry of life. But their fire carries another truth, darker, more absolute, the power to erase. Entire species, ecosystems, and climates have been reshaped, rewritten, and sometimes obliterated by volcanic fury. Volcanoes are not only creators, they are destroyers, architects of extinction on a planetary scale. The story begins over 250 million years ago, during the Permian period, when the largest mass extinction in Earth's history unfolded. Known as the Great Dying, this event erased more than 90% of marine species and 70% of terrestrial species. The cause was not a single asteroid or comet, but a series of cataclysmic volcanic eruptions from the Siberian Traps, an immense flood basalt province in what is now Russia. Lava poured endlessly across the landscape, covering millions of square kilometers, releasing toxic gases and triggering climate chaos. These eruptions were monumental in every sense. Rivers of molten rock spread across the land, burying forests, rivers, and habitats. Carbon dioxide and methane flooded the atmosphere, turning Earth into a greenhouse inferno. Temperatures rose dramatically, oceans acidified, and anoxic conditions suffocated marine life. Volcanic eruptions of this scale transformed the planet itself, altering the chemistry of air, sea, and soil, and leaving scars that can still be traced in the geologic record. Volcanism has punctuated other critical moments in Earth's history. The Deccan Traps in India, erupting around 66 million years ago, coincided with the extinction of the dinosaurs. While an asteroid impact at Chicxulub contributed to the devastation, the Deccan eruptions released vast quantities of gases, ash, and aerosols, altering the climate and destabilizing ecosystems worldwide. Volcanic activity can amplify catastrophe, creating conditions in which even the mightiest species become vulnerable. It is not only the global scale that is terrifying, but the speed with which volcanoes can alter the world. In a matter of years, a geological heartbeat, ecosystems collapse, species vanish, and climates shift. The magnitude of these events dwarfs any human disaster, reminding us that the Earth operates on a scale far beyond human comprehension. Volcanoes, in their fury, are indifferent to life. They obey only the physics of molten rock, pressure, and gas. Consider Tambora in 1815, one of the most famous historic eruptions. While small in comparison to the Siberian or Deccan Traps, Tambora caused global upheaval. Its ash cloud circled the planet, blocking sunlight and triggering the year without a summer. Crops failed across Europe and North America, famine spread, and disease followed. Even a single eruption, when properly positioned and powerful enough, can ripple across the world, altering human history and reminding us that volcanic power does not respect borders, nations, or empires. Supervolcanoes, with calderas spanning tens of kilometers, are the ultimate expression of this destructive potential. Yellowstone, Toba, Ira. These names evoke both scientific fascination and existential dread. Toba, in Indonesia, erupted roughly 74,000 years ago in a cataclysm that may have nearly annihilated humanity itself. Scientists estimate that global temperatures dropped dramatically, and genetic evidence suggests a bottleneck in human populations. Volcanoes, in such moments, are forces that shape the trajectory of life, forcing evolution to adapt or perish. The record of volcanic destruction is also a record of human resilience. Ancient civilizations rebuilt after Tambora and Vesuvius. Survivors adapted to ash-laden soils and hazardous slopes. Humanity, for all its vulnerability, learned to coexist with fire, observing patterns, recording eruptions, and eventually developing methods to predict and prepare. Volcanoes, then, are both teachers and challengers, demanding respect while offering lessons in survival, patience, and adaptation. While volcanoes have the power to destroy, they are equally forces of creation. Their fire and molten rock, their ash and gases, are not only agents of catastrophe, but architects of possibility. In the quiet aftermath of eruption, they lay the foundations for life, creating habitats, enriching soils, and shaping the chemistry that allows life to flourish. On the early Earth, long before humans appeared, volcanic activity played a central role in making the planet habitable. The Hadean and Archean eons were dominated by relentless eruptions which released water vapor, carbon dioxide, and nitrogen into the atmosphere. These gases slowly form the primordial air, which would one day allow clouds to form, rain to fall, and oceans to gather. Volcanoes were the first breath of the planet. Beneath the oceans, volcanic activities sculpted entirely new worlds. Hydrothermal vents, deep-sea geysers spewing mineral-rich fluids, created chemical oases in the darkness. Here, far from sunlight, life could emerge. The mixing of superheated water with cold ocean currents created gradients of temperature and chemistry, producing an energy source independent of the sun. In these extreme conditions, molecules may have assembled into the first protocells, setting the stage for life to evolve. Volcanoes also foster biodiversity through isolation. Volcanic islands, separated from continental lands, become laboratories of evolution. Species adapt to their unique environments, developing traits that distinguish them from their mainland relatives. Darwin observed this firsthand in the Galapagos, where volcanic islands revealed the power of isolation and environmental pressure to shape life. Volcanoes create not just habitats, but crucibles of evolutionary innovation. The interplay between destruction and creation is evident in ecosystems shaped by volcanic disturbance. Lava flows reset landscapes, clearing forests, creating new lakes, and redirecting rivers. Ash deposits enrich soils and waterways. Species that survive eruptions often exploit the new conditions, while others perish. Volcanoes also regulate planetary systems essential for life. Carbon dioxide released by eruptions contributes to the greenhouse effect, maintaining temperatures that allow liquid water to exist. Sulfur gases, though sometimes toxic, play a role in atmospheric chemistry, influencing rainfall patterns and nutrient cycles. Even the cooling of lava releases heat into the surrounding environment, subtly affecting local climates. Volcanoes are not merely localized phenomena. They are integral to the global systems that sustain life. Consider the extraordinary ecosystems around modern hydrothermal vents. Giant tube worms, crabs, and shrimp thrive in waters exceeding 400 degrees Celsius, nourished by chemosynthetic bacteria that convert volcanic chemicals into energy. These creatures demonstrate that life can exist without sunlight, drawing sustenance directly from the planet's molten heart. Volcanoes, in this sense, create worlds within worlds, niches where life adapts in astonishing ways. Volcanic islands also provide insight into the long-term shaping of life. The Hawaiian Islands, emerging over a stationary hotspot, are a living timeline of volcanic activity and ecological succession. Older islands, eroded and subsiding, host mature forests and complex ecosystems. Younger islands are dominated by pioneer species, struggling to colonize fresh lava flows. Here, volcanoes act as architects of time, their eruptions creating a living laboratory in which evolution unfolds before our eyes. Volcanoes also shape life through climate and hydrology. Their eruptions inject aerosols and gases into the atmosphere, influencing rainfall, temperature, and weather patterns. Lava flows carve rivers, build mountains, and form calderas that collect fresh water. In these ways, volcanoes dictate the distribution of habitats, the availability of resources, and the opportunities for life to flourish. They are silent engineers, sculpting the world on scales both local and global. Volcanoes have always loomed over human history, their presence both feared and revered. They are mountains of fire that shape landscapes, dictate settlement patterns, and command respect. Humanity's relationship with volcanoes is complex. We are drawn to them for the fertile lands they create, yet haunted by the destruction they can unleash. Civilization has risen and fallen in their shadows, shaped by the slow, relentless power of molten earth. The earliest settlements often chose locations near volcanic soils, unaware of the latent danger beneath their feet. These soils, rich in minerals, provided unparalleled fertility. Crops flourished where lava had once flowed and ash had settled, producing harvests that could sustain entire populations. In regions such as Java, the Andes, and the Mediterranean, human civilization owed its survival to the very fire that could annihilate it. Volcanoes, in this way, became silent partners in the story of human development. The shadow of Vesuvius is perhaps the most famous testament to the duality of volcanic power. In 79 CE, the eruption buried Pompeii and Herculaneum beneath meters of ash and pumice. For the inhabitants, it was instantaneous catastrophe. For future generations, it became a window into Roman life. Archaeologists have unearthed streets, homes, and frescoes preserved with astonishing clarity, revealing not only the fragility of human existence, but also the capacity for memory and reflection that arises from such events. The city was destroyed, yet through its destruction, it has endured, a paradox only volcanoes can orchestrate. Beyond destruction, volcanoes have influenced culture, religion, and mythology. Across the globe, fire mountains became sacred spaces. The Hawaiians worshipped Pele, goddess of volcanic fire, who both created and destroyed islands. In Japan, Mount Fuji inspired art, poetry, and pilgrimage, a symbol of beauty intertwined with potential danger. In Italy, Vesuvius loomed over Naples, feared yet revered as a powerful natural entity. Volcanoes shake the human imagination as much as they shape the physical world, influencing the stories we tell, the rituals we perform, and the meaning we ascribe to existence. Agriculture near volcanoes reveals another layer of human adaptation. The mineral-rich soils of volcanic regions produce crops that are unmatched elsewhere. Coffee, tea, sugarcane, and a multitude of vegetables thrive in these lands. Civilizations learn to cultivate these soils with care, balancing the risk of eruptions with the benefits of abundance. In this way, volcanoes directly shaped economies, settlement patterns, and societal development. Fertility emerged from destruction, and humans learned to read the rhythms of fire as a guide to survival. Volcanoes have also shaped urban development and disaster preparedness. In regions like Japan, Indonesia, and Italy, cities have developed sophisticated systems to monitor volcanic activity. Early warning systems, evacuation plans, and zoning laws are modern adaptations to an ancient challenge. Human ingenuity meets natural power, acknowledging that while volcanoes cannot be controlled, their impact can be anticipated and mitigated. Civilization, in this sense, is both shaped by and resilient to volcanic activity. Volcanoes have inspired art, architecture, and literature. Painters have depicted eruptions with awe-inspiring detail, capturing the interplay of light, fire, and ash. Writers and poets have drawn metaphor and meaning from volcanic power, using eruptions as symbols of transformation, destruction, and renewal. Even architecture reflects the challenge. Buildings in volcanic regions are designed with resilience in mind, incorporating knowledge gleaned over centuries. Volcanoes, in every form, influence human creativity. Religious and spiritual practices often reflect the presence of volcanoes. Sacrifices, offerings, and prayers were made to appease the fiery forces, recognizing their potential for both creation and destruction. In this way, volcanoes shaped not only physical survival, but the moral and cultural frameworks through which communities interpreted the world. They were both feared and honored, omnipresent in the moral and spiritual imagination of civilizations. Trade and migration patterns were also influenced by volcanic landscapes. Fertile volcanic soils supported dense populations, creating hubs of commerce. At the same time, eruptions and lava flows forced migrations, shaping the movement of peoples and the spread of cultures. Human history, in many regions, is intertwined with the rhythms of fire, demonstrating that volcanoes are not merely geological features, but active participants in the story of civilization. The study of volcanoes also advanced science, directly shaping human knowledge, Pliny the Younger's account of Vesuvius was among the first systematic observations of an eruption. Later, during the 18th and 19th centuries, scientists like Humboldt and Lyell studied volcanic processes, linking eruptions to geological phenomena and laying the foundation for modern volcanology. Human survival, culture, and curiosity have been intertwined with these mountains of fire, driving both practical adaptation and intellectual discovery. Volcanoes, ancient and eternal, continue to command humanity's awe. Though science has illuminated their rhythms and forces, the fire beneath the earth remains unpredictable, patient, and indifferent. The challenge of the modern age is not to conquer these mountains of fire, but to understand them, to predict their movements, and to coexist with their immense power. Modern volcanology is the culmination of centuries of observation, theory, and technological innovation. The field combines geology, chemistry, physics, and computer modeling to decipher the hidden signals that precede an eruption. Volcanoes, once inscrutable and terrifying, can now be studied in real time, their activity monitored through instruments that detect the subtlest shifts in the Earth's crust. Seismology is central to this endeavor. Volcanoes are restless, their molten interiors generating tremors long before they erupt. Sensitive seismographs detect these microquakes, mapping the movement of magma through chambers and conduits beneath the surface. Patterns emerge. Swarms of earthquakes often precede eruptions, signaling the planet's molten pulse. By listening carefully, scientists can forecast danger and issue warnings that save thousands of lives. Gas monitoring is another key tool. Volcanoes release carbon dioxide, sulfur dioxide, and other volatile compounds as magma rises. Sudden increases in these emissions can indicate that magma is approaching the surface. Remote sensing and satellite technology have revolutionized our understanding of volcanoes. Thermal imaging detects heat anomalies, while radar and LiDAR measure ground deformation with millimeter accuracy. Volcanoes often swell as magma accumulates, and satellites can observe these changes from space. This integration of observation, measurement, and prediction marks a new era in which humanity can anticipate the movements of forces once deemed uncontrollable. Computer modeling further enhances our predictive capacity. Complex simulations replicate magma flow, eruption dynamics, and ash dispersal, allowing scientists to forecast the potential impact on communities, air traffic, and ecosystems. Models are informed by historical data, laboratory experiments, and ongoing field measurements. While uncertainty remains, yet prediction is only part of the challenge. Protecting human life and property requires infrastructure, planning, and public education. Evacuation routes, hazard maps, and early warning systems have become essential components of civilization in volcanic regions. Countries like Japan, Indonesia, Italy, and the Philippines have invested heavily in monitoring networks and disaster preparedness, translating scientific insight into practical safety measures. Volcanoes, while still powerful, no longer strike without warning. The future of volcanology is also intertwined with climate and planetary change. Volcanoes influence the atmosphere, injecting aerosols and gases that affect weather patterns and global temperatures. Understanding these interactions is crucial, not only for predicting eruptions, but also for modeling climate change. Large eruptions can temporarily cool the planet, as seen after Tambora in 1815, while continuous degassing contributes to greenhouse warming. Emerging technologies promise even greater insights. Drones fly directly into ash plumes, sampling gases and capturing high-resolution imagery. Autonomous underwater vehicles explore hydrothermal vents and submarine volcanoes, revealing processes that were once inaccessible. Artificial intelligence analyzes seismic data, gas emissions, and satellite imagery, detecting subtle signals invisible to human observers. The fire of the Earth, once mysterious and untamed, is increasingly legible through the lens of modern science. Yet, for all our knowledge, the humility demanded by volcanoes persists. No prediction is perfect, no system infallible. Volcanoes are ancient storytellers. Their eruptions, lava flows, and ash clouds speak across time, narrating the history of Earth long before humans appeared. In their fire, one can read the earliest chapters of our planet, the forging of continents, the shaping of oceans, the birth of life itself. They are at once destructive and creative, a duality that reflects the very essence of existence. To witness a volcano is to confront the paradox of life and death intertwined. Lava consumes forests, towns, and landscapes, yet from the ashes emerge fertile soils, new habitats, and the possibility of renewal. Humanity's place in this narrative is both fragile and resilient. Volcanoes have destroyed civilizations and displaced populations, yet they have also nurtured agriculture, inspired mythology, and shaped the imagination. Cities have been buried and rebuilt. Cultures have risen in the shadows of fire. Societies have adapted, innovated, and endured. We are small actors on a stage of molten rock and atmospheric fury, yet through observation, ingenuity, and respect, we persist. The duality of volcanoes mirrors the duality of existence itself. Life is born in vulnerability and thrives amidst chaos. Evolution, like volcanic activity, is driven by both catastrophe and renewal. Species perish in eruptions, yet survivors adapt, migrate, and diversify. Volcanoes remind us that time is measured differently on the scale of Earth. Human lifetimes are fleeting, mere heartbeats against the slow pulse of tectonic movement and the gradual cooling and eruption of magma. Mountains rise and erode, islands emerge and sink, and the Earth reshapes itself with patient indifference. In this perspective, human achievement is both extraordinary and ephemeral, a brief moment in the vast theater of planetary processes. The creative power of volcanoes extends beyond biology and civilization. They sculpt landscapes of extraordinary beauty, towering peaks, jagged lava fields, and islands rising from the sea. Even in death and destruction, volcanoes inspire reflection. The ruins of Pompeii, Herculaneum, and countless other settlements evoke a haunting awareness of impermanence. Ash preserves as much as it destroys, capturing moments of human life, frozen in time. These events remind us of our vulnerability, the fleeting nature of civilization, and the enduring power of natural forces. Fire is a teacher of mortality, urging reverence and mindfulness. In this light, volcanoes are not merely geological phenomena. They are mirrors of existence. They reflect creation and destruction, persistence and impermanence, order and chaos. Life, civilization, and even human consciousness are shaped by forces that predate us and will outlast us. Volcanoes remind us that we are part of a continuum, participants in a story that spans billions of years, where fire and water, rock and air, chance and necessity intersect to produce the improbable phenomenon of life. Volcanoes also illuminate the balance of risk and reward. Fertile soils, abundant resources, and scenic landscapes attract human settlement, yet the threat of eruption persists. Humanity has learned to negotiate this balance, building resilient structures, developing early warning systems, and cultivating agricultural knowledge. The same fire that can destroy also sustains life, reminding us that coexistence requires respect, knowledge, and preparation. On a spiritual and emotional level, volcanoes evoke awe and contemplation. They are monuments to the planet's vitality, expressions of energy that predate and exceed human existence. Witnessing an eruption or observing volcanic landscapes can evoke feelings of humility, wonder, and connectedness. Fire, molten and relentless, embodies the tension between creation and annihilation, between beauty and terror. In this, volcanoes communicate truths that transcend words, reaching directly into human consciousness. Beneath the tranquil veil of landscapes we often take for granted, fire sleeps. It lies hidden in the bowels of the earth, a restless force, patient yet inexorably powerful. Volcanoes are not merely mountains of stone or channels of molten rock. They are the Earth's pulse made visible, the primal rhythm of creation and destruction. Every eruption, every lava flow, every ash-laden wind is both a punctuation and a prelude, a reminder that life and death are inseparable in the grand narrative of our planet. From the fertile valleys of Java to the volcanic highlands of the Andes, humanity has learned to dwell beside these molten giants. The soils that emerge from volcanic deposits are unlike any others, rich in minerals, imbued with phosphorus, potassium, and trace elements essential for plant growth. Fields of rice flourish on weathered volcanic soils. Vineyards flourish on the slopes of Vesuvius, and orchards spread across the islands of Sicily. Life, in its quiet persistence, has adapted to harness fire's residue. Volcanic soils act as incubators of fertility, offering abundance to those who live in their shadow. For millennia, civilizations have thrived in proximity to these mountains, drawn by the promise of abundance, yet always aware of the lurking peril. Yet, the same forces that nurture also possess the capacity for annihilation. Pyroclastic flows surge with unimaginable speed and heat, obliterating everything in their path. Ash clouds can encircle the globe, darkening skies and cooling climates for years. The eruption of Tambora in 1815 cast a pall over much of Europe and Asia, causing crop failures and famine, an event remembered as the year without a summer. Krakatoa in 1883 sent shockwaves through the atmosphere and oceans, the sound audible thousands of kilometers away. Volcanoes remind us in both whispers and roars of the tenuousness of human existence, of how intimately our survival is tied to the moods of the earth itself. This duality, creation and destruction entwined, is reflected not only in human history, but in the very evolution of life. Hydrothermal vents, born from underwater volcanic activity, offer one of the most compelling windows into life's origins. In these extreme environments, where molten rock meets cold seawater, life first found a foothold. Chemosynthetic bacteria extract energy from mineral-rich fluids, forming the base of ecosystems that exist entirely without sunlight. Here, in the incandescent cradle of fire, the earliest chapters of life unfolded, teaching us that survival often emerges from the harshest conditions. Volcanoes also act as agents of evolutionary pressure. Each eruption, each shifting lava field, forces life to adapt or perish. Species on volcanic islands, from insects to birds, develop specialized traits in response to the sudden creation of new terrain or the obliteration of old. The Galapagos, a chain of islands born entirely from volcanic activity, illustrates this principle vividly. The human narrative mirrors this duality. Pompeii and Herculaneum, forever frozen beneath the ash of Vesuvius, are stark reminders of our vulnerability. Entire communities, thriving in the shadow of a volcano, were erased in hours, yet preserved in a way that allows us to glimpse into the past. Volcanic catastrophes have repeatedly punctuated history, reshaping societies, economies, and even climate patterns. Modern science has deepened our understanding of this duality. Geologists study the mineral composition of volcanic soils to predict fertility patterns. Volcanologists monitor seismic activity, gas emissions, and ground deformation to forecast eruptions. Satellites orbit the Earth, mapping hotspots and thermal anomalies, while drones explore craters and fumaroles inaccessible to humans. The knowledge accumulated allows us to anticipate, mitigate, and to some extent, harness volcanic power. Yet, despite all our tools, the essence of a volcano, its capricious and awe-inspiring force, remains beyond complete mastery. Within the superheated embrace of these vents, Minerals such as iron, nickel, and sulfur catalyzed reactions that generated the first organic molecules. Amino acids, lipids, and nucleotides, precursors to proteins and RNA, emerged from the turbulence, forming membranes, chains, and primitive metabolic networks. The contrast of extreme heat and the cold abyss of corrosive chemicals in gentle diffusion provided the energy gradients that early life required. Here, in the crucible of Earth's inner fire, the first organisms discovered the alchemy of existence. These microbial pioneers were remarkable not only for their resilience, but for their adaptability. Chemosynthetic bacteria, which today still thrive in hydrothermal vents, converted inorganic compounds into energy without the need for sunlight. They were among the first to exploit the duality of their environment, the destructive heat of volcanic effluent, and the life-giving nutrients it carried. Their survival demonstrated a principle that echoes through geological time. Life does not merely endure, it adapts, thrives, and evolves in response to the forces that surround it. The influence of volcanic activity extended far beyond the seafloor. Volcanic outgassing, the release of carbon dioxide, nitrogen, and water vapor, helped shape Earth's early atmosphere, establishing the conditions necessary for future complex life. Periodic eruptions, both beneath the ocean and on the land, recycled minerals and redistributed nutrients across the planet, providing the fertile substrate upon which ecosystems could emerge. Every eruption, every plume of volcanic gas contributed subtly to the evolving story of life, reminding us that creation and destruction are inseparable companions in the unfolding of planetary history. The cycles of volcanic activity created environments that were at once perilous and generative. Island arcs and volcanic highlands emerged from molten rock, offering new niches for colonization. Lava flows cooled to form fertile soils, capable of supporting plants and later entire terrestrial ecosystems. Here too, life's story unfolded as a balance between risk and reward. Species were compelled to migrate, adapt, or perish, each eruption reshaping the evolutionary landscape in profound ways. Volcanoes also left their mark in more subtle forms, etched into the geochemistry of the early Earth. Layers of basalt and ash preserve traces of ancient eruptions, recording not only the planet's fiery temper, but also the chemical composition of oceans and atmosphere at the time. By studying these geological archives, modern scientists reconstruct the environmental conditions in which early life emerged, revealing a dynamic interplay between Earth's inner heat and the fragile molecules that would become the first living systems. The dual nature of volcanoes as both destroyers and creators resonates in these early chapters of life. They offer warmth and nutrients in one breath, yet pose lethal hazards in the next. This paradox is mirrored in the biology of life itself. Organisms that endure volcanic environments often develop extraordinary resilience, leveraging the very forces that could annihilate them. From extremophiles in hydrothermal vents to plants thriving on volcanic soils, life demonstrates an intimate knowledge of how to coexist with fire. Yet the philosophical weight of volcanic influence extends beyond biology. Volcanoes remind us that creation is rarely serene. It is forged in tension, in the crucible of opposing forces. Life emerged not in quiet stability, but in the turbulence of heat, pressure, and chemical flux. Each microbial colony, each strand of RNA that survived the scalding waters of early Earth, is a testament to the capacity of existence to persist against formidable odds. Volcanoes, in shaping the chemistry of oceans, even today, the echoes of these ancient processes persist. Hydrothermal vents teem with organisms that trace their lineage back to the earliest extremophiles. Volcanic soils continue to nourish plants and sustain humans. Across the millennia, human civilizations have grown in the shadow of fire. Mountains that erupt with molten fury have drawn both reverence and fear, shaping the course of culture, settlement, and survival. The duality of volcanoes, as creators of fertile land and agents of sudden destruction, has defined the rhythm of human history, teaching lessons in adaptation, resilience, and humility. Volcanic soils are among the most productive on Earth. Weathered layers of basalt, pumice, and ash release essential nutrients slowly over time, providing an enduring richness that sustains agriculture. Ancient societies, from the valleys of Java and the highlands of Mexico to the slopes of Vesuvius and Etna, harnessed this fertility to cultivate crops that fed growing populations. Rice terraces in Indonesia cling to volcanic slopes, while vineyards on Mount Vesuvius thrive in soil enriched by centuries of eruptions. Even today, these soils offer a paradoxical gift: life sustained by the very forces that threaten to annihilate it. Yet with abundance comes vulnerability. Human settlements near volcanoes have always balanced the lure of fertility with the specter of catastrophe. In 79 CE, Mount Vesuvius erupted with terrifying swiftness, burying Pompeii and Herculaneum under meters of ash. Entire communities were erased in hours, preserving in death a frozen snapshot of life at that moment. The markets, the homes, the streets. These cities, once centers of human activity, became cautionary tales, reminding humanity of its fragility in the face of forces far beyond control. Volcanic eruptions have repeatedly shaped the course of civilizations. The eruption of Tambora in 1815, one of the largest in recorded history, released vast volumes of ash and aerosols into the atmosphere, triggering the year without a summer. Crops failed across Europe and Asia, famine spread, and populations suffered as societies struggled to respond to environmental upheaval. Krakatoa in 1883 sent shockwaves around the globe, demonstrating that the consequences of volcanic activity extend far beyond local landscapes. Volcanoes, in their eruptions, impose lessons in humility, showing the limits of human foresight and the delicate balance of survival. Yet humans have not merely been victims. Over centuries, societies have developed ways to coexist with these fiery neighbors. Early warning practices, observation of volcanic signs, such as fumarole activity, minor tremors, and changes in vegetation, enabled communities to anticipate danger. Religious rituals, myths, and oral histories encoded knowledge about volcanic hazards, offering early forms of hazard management. Volcanoes became both objects of worship and subjects of science, blending awe with empiricism in the human quest to understand the world. The interplay of destruction and creation in human civilization mirrors the geological processes beneath the surface. Lava flows and ash deposits reshape landscapes, altering rivers, valleys, and coastlines. These changes, in turn, influence patterns of settlement, migration, and agriculture. In Japan, volcanic islands such as Sakurajima have continuously challenged communities, yet their fertile soils sustain dense populations. In Central America, the highlands of Guatemala and Mexico are dotted with towns and cities that owe their existence to volcanic fertility, even as they lie in the shadow of potentially catastrophic eruptions. Human history is inseparable from the dynamic forces that shape the land beneath our feet. Volcanoes also influence culture, art, and mythology. The destructive power of Mount Vesuvius inspired early Roman accounts, while Japanese Shinto reverence for volcanic peaks like Mount Fuji embodies both spiritual awe and practical respect. Hawaiian legends honor Pele, the goddess of fire, illustrating the intimate connection between human identity and volcanic landscapes. These narratives encode the duality of volcanoes, agents of both fear and sustenance, capable of obliteration and creation. Through art, literature, and ritual, humans. Volcanoes, in their most extreme forms, transcend local landscapes. They are not merely mountains of molten rock. They are planetary architects, capable of reshaping climate, ecosystems, and human civilization across continents. Supereruptions, events of such magnitude that they dwarf ordinary volcanic activity, remind us that Earth's internal fires operate on scales both vast and terrifying, influencing not only the land beneath our feet, but the very atmosphere that envelops the planet. The concept of a supereruption challenges our ordinary perception of volcanic power. Unlike typical eruptions, which affect regional areas, supereruptions release thousands of cubic kilometers of magma and ash into the sky, blanketing the globe in a veil of particulate matter. The Toba eruption, approximately 74,000 years ago, expelled an estimated 2,800 cubic kilometers of volcanic material, producing a volcanic winter that may have lowered global temperatures by several degrees Celsius for years. Evidence from ice cores and sediment layers suggests that such events create conditions severe enough to threaten ecosystems, crop production, and, in extreme cases, human survival. These eruptions operate on timescales that dwarf human experience, yet their consequences are immediate and catastrophic. Pyroclastic flows surge with lethal speed, obliterating everything in their path. Ash clouds rise into the stratosphere, dispersing fine particles that can circumnavigate the globe, reflecting sunlight and cooling the planet. Volcanic gases, rich in carbon dioxide and sulfur dioxide, chemically alter the atmosphere, influencing precipitation, altering ocean chemistry, and triggering feedback loops that can last for years. In these moments, volcanoes reveal themselves not merely as geological phenomena, but as forces capable of influencing the trajectory of life on Earth. Supereruptions also offer insight into the deep processes of the planet. Massive magma chambers, often tens of kilometers wide, accumulate pressure over tens or hundreds of thousands of years. Heat and buoyancy drive the slow ascent of molten rock, while fractures in the crust determine the eventual pathways of eruption. Seismographs detect the subtle rumblings of magma movement. Gas analyzers monitor the release of sulfur dioxide, and satellites track deformation of the land surface. Each measurement uncovers the hidden mechanics of these planetary events, yet the precise timing of a supereruption remains unpredictable, a humbling testament to the complexity of Earth's interior. The climatic consequences of supereruptions illuminate the profound interconnectedness of Earth systems. The release of ash and aerosols into the stratosphere reduces the amount of sunlight reaching the surface, cooling global temperatures and triggering the disruption of agricultural cycles. Historical eruptions, such as Tambora in 1815, caused crop failures, famine, and social unrest. Scientists hypothesize that ancient supereruptions may have contributed to population bottlenecks in human evolution, shaping the genetic diversity of modern humans. These events demonstrate that volcanoes, while localized in origin, can exert influence on a planetary scale, linking geology to biology, atmosphere to survival. Modern science seeks to understand and anticipate these events, though the challenge is immense. Yellowstone, Toba, and other supervolcanic sites are carefully monitored, yet the enormity of the forces involved leaves a margin of uncertainty. Geologists analyze caldera formations, study tephra deposits, and measure ground deformation to estimate potential activity. High-resolution satellite imagery tracks subtle bulges in the crust, and gas emissions are continuously measured to detect early signs of unrest. While prediction has improved, the sheer scale and complexity of supereruptions ensure that complete certainty remains beyond reach. Supereruptions are not only destructive, they are profoundly creative. Lava flows and ash layers sculpt new landscapes, enrich soils. Beneath the surface of the Earth, in the dark crucible of the mantle, Forces gather that are both ancient and ceaseless. The heat, pressure, and motion of these deep regions give rise to volcanoes, the visible expression of processes that are otherwise hidden from human sight. Understanding these processes requires not only observation, but imagination, the ability to infer the invisible, to trace the subtle signs of motion through rock and gas, to speculate with rigor on forces that operate on scales far beyond ordinary perception. In this chapter, volcanoes become a window into planetary mechanics, revealing the complex interplay of mantle dynamics, plate tectonics, and deep Earth chemistry. The theory of plate tectonics, formulated in the mid-20th century, provides the framework for understanding much of volcanic activity. Earth's lithosphere is fragmented into plates that float atop the convecting mantle. At divergent boundaries, plates pull apart, allowing magma to rise and form new crust. At convergent boundaries, subduction zones carry one plate beneath another, melting rock and triggering explosive volcanism. The Pacific Ring of Fire, a vast arc of volcanic and seismic activity, exemplifies these dynamics. Volcanoes along this belt are not isolated. They are the surface expression of deep, planetary-scale motions. Lava, ash, and pyroclastic flows are but the final act of a drama that begins hundreds of kilometers below the surface. Mantle plumes offer another layer of explanation, illuminating the origin of volcanoes far from tectonic boundaries. These plumes are columns of anomalously hot rock that rise from the deep mantle, melting the overlying lithosphere and producing volcanic islands such as Hawaii and Iceland. The hotspots they create are stationary relative to moving plates, leaving a trail of volcanic activity that records the motion of continents over geological time. Through this lens, the Earth itself becomes a narrative in stone, a story etched by fire, tracing patterns of motion and energy flow over tens of millions of years. Volcanic chemistry provides further insight into the processes shaping eruptions. Magma composition determines the style, intensity, and consequences of an eruption. Basaltic magma, low in viscosity, tends to produce gentle flows, forming shield volcanoes that spread across landscapes in broad arcs. Andesitic and rhyolitic magmas, rich in silica, are more viscous and prone to explosive eruptions, generating towering plumes of ash and pyroclastic flows. By analyzing mineral content, trace elements, and isotopic ratios, scientists can reconstruct magma genesis, infer mantle source regions, and predict eruption behavior. Each chemical signature is a clue, a whisper from the depths of the planet, revealing patterns that span millennia. Beyond Earth, comparative planetology offers speculative yet credible insight into volcanic processes. Io, Jupiter's moon, is a world of relentless eruption, its surface sculpted by molten lava and sulfur flows far more extreme than anything on Earth. Mars's Olympus Mons, a shield volcano of unimaginable scale, suggests prolonged volcanic accumulation under different gravity and atmospheric conditions. Venus, with its volcanic plains and vast lava channels, hints at planetary volcanism operating under a dense, greenhouse-laden atmosphere. These analogues reinforce the universality of volcanism as a planetary process. The movement of heat and material from interior to surface, shaping landscapes, climates, and potentially conditions for life. The speculative edges of volcanology extend to the early Earth and the origins of life. Large-scale volcanic activity, including supereruptions and flood basalts, likely influenced atmospheric composition, ocean chemistry, and global climate. Hydrothermal systems, powered by volcanic heat, may have provided the energy and chemical gradients necessary for the emergence of life. Even on other worlds, volcanic activity may offer the conditions for habitability, heating subsurface oceans, cycling nutrients, and producing chemically rich environments capable of supporting life. Volcanoes, in this sense, are both engines of planetary evolution and catalysts for biological possibility. Volcanoes, for all their visible majesty, conceal their true nature beneath layers of rock, sediment, and molten rock. To understand these forces, humans have developed tools that allow us to peer into their hidden depths, to read the subtle signs of unrest, and to anticipate their mood swings before catastrophe strikes. Modern volcanology is a marriage of observation, measurement, and predictive modeling, a testament to humanity's capacity to interpret the silent language of fire. Seismology forms the foundation of volcanic monitoring. Earthquakes, both minor tremors and larger foreshocks, often herald magma movements deep beneath the crust. Seismometers, distributed across volcanic regions, detect vibrations imperceptible to humans, translating them into patterns that reveal the ascent of molten rock. By mapping these signals in 3 dimensions, volcanologists can locate magma chambers, estimate pressure buildup, and anticipate eruption potential. Each tremor is a whisper from the deep, a message encoded in the language of rock and vibration. Deformation monitoring complements seismology. GPS networks, tiltmeters, and satellite-based radar interferometry measure the subtle swelling or subsidence of volcanic edifices. Magma rising through conduits distorts the surrounding crust, inflating the surface by centimeters or even meters. By observing these shifts over days, months, and years, scientists can infer the size and movement of subterranean magma bodies. Such precision allows for early warning, providing communities with critical time to evacuate. Gas emissions provide yet another vital clue. Volcanoes exhale a mixture of carbon dioxide, sulfur dioxide, water vapor, and other gases, which vary in composition and volume as magma evolves. High concentrations of sulfur dioxide, for instance, can signal the ascent of new magma toward the surface, while changes in carbon dioxide flux may indicate pressurization within the magma chamber. Modern spectrometers, drones, and satellite instruments measure these emissions continuously, translating chemical signals into actionable data. Each plume is a narrative of subterranean processes, revealing the hidden life of a volcano. Recent advances in drone technology have revolutionized volcanic monitoring. Unmanned aerial vehicles can approach active craters, fly above molten lava, and navigate hazardous terrain, capturing high-resolution imagery and chemical data that would be impossible to obtain safely otherwise. Drones provide unprecedented detail on eruption dynamics, from the behavior of lava fountains to the evolution of volcanic plumes, creating a bridge between human observation and the inaccessible heart of the volcano. Beyond immediate safety, monitoring volcanoes deepens our understanding of planetary processes. Subsurface studies, including drilling and geophysical imaging, reveal the architecture of magma chambers, the mechanics of hydrothermal systems, and the thermodynamics of volcanic conduits. These insights inform broader theories of mantle convection, plate tectonics, and planetary evolution. Volcanoes, observed meticulously through these tools, become laboratories of deep earth science, connecting surface phenomena to the forces that shape the planet over eons. Historical eruptions provide context for these modern tools. The 1980 eruption of Mount St. Helens demonstrated both the destructive power of volcanoes and the value of rigorous monitoring. Pre-eruptive signs, seismic swarms, ground deformation, and gas emissions were recorded in detail, allowing scientists to study eruption precursors with unprecedented clarity. Lessons from Mount St. Helens. Helens and subsequent eruptions worldwide have informed early warning systems, guiding policy, infrastructure, and public awareness. Each instrument, measurement, and model is part of an evolving effort to understand volcanoes not as distant spectacles, but as dynamic systems with direct consequences for life and civilization.